Unboxing.
Is that the router they have on the table out there?
No, that's mine. I brought that from home. I hardly ever use them because I can run a motor and check it, but I want to talk a little bit about how to do that.
Yeah, good.
Yeah.
Intentionally, because I had a couple fans I want to send you.
Well, 5 minutes, we'll get started.
I'll record about 5 minutes.
For you. If you come up with a question during the presentation, open your hands, raise up your hands, and just, I'll call on you and we can answer your question, and I'm sure that will help us give us more, make our talk even better. No such thing as a stupid question, so don't worry. Just ask it and we'll answer it. I want to start off a little bit by talking about electrical safety. We'll take about 5 minutes on that because electricity is dangerous. And I want to tell you, if you get 5 milliamps, that's 5 1,000ths of an amp across your chest, it'll take you out. So when working with electricity, what I recommend you do in your shop is start out and get yourself a ground fault interrupter outlet at your workbench. And what that ground fault interrupter does is it measures the amount of current going out one wire and coming back the other wire. And if the ground fault interrupter sees a discrepancy in that, because you're working on your fan or your motor, and you touch this, and you forgot to put your shoes on, and you're standing on the wet basement floor or damp basement floor, it will just tell that you've got current going through your body, and it will shut the power off. Now, don't rely on that as 100% fail-safe. We still need to practice electrical safety. It's just one thing that can help protect you. Another nice thing to have is an arc fault breaker. This is something that the National Electrical Code is requiring in all new home construction for residential areas in the home. And what an arc fault breaker does is, say for example, you hit 2 leads together. You've seen the fireballs. Who's made a big fireball in their shop? We all have. You'll get a small spark and it will kill the power. Another nice thing about that is you've got your fan, you just brought it home from the flea market, and you're turning it on and there's a short in the head wire. You're not going to weld your contacts together. Anyone ever welded a set of contacts together in a switch? There you go. That'll help save that. We're going to take that a little further. Those are 2 things I'd recommend that you do have. And when you are working with electricity, and the power's on, you got your alligator clips out, and you're going to hook this up, one hand behind the back, That way, you're eliminating that chance of electricity going across your chest. That's the one thing that can really kill you. Another thing that can happen is, if you come in contact with electricity, it can actually cause your muscles to contract, and you could be holding onto something and it becomes hot, and you'll clamp down on it with your hands and you can't let go. So another rule, never work alone. Have your wife within earshot or somebody or a friend. If you're not, and above all else, if you're not comfortable working with electricity, don't do it. There's a lot of people in this club that will be happy to help you. Go over to their house. Come over to my house, call me up and say, hey Bill, I'd like to stop by. You're all welcome to stop by and we'll work on things together and I'll show you a few things. But be safe, that's all I can say. All right, I want to show you a really cool tool that we all need to have. And I hope that it's still inside my toolbox. This is a fingernail cutter. You want to buy one of these and take the lever off of it. And you probably all encountered magnet wire. It's got varnish on it or it's corroded. And you want to solder that wire. You try cleaning it up and you break it. This is the best tool for that application. What you can do is you can take that magnet wire and you can just scrape it with this, and it will scrape it up to nice pure copper, so it's really easy to solder. Best tool you'll ever have.
Just lightly squeezing on it.
Right? Squeeze it, drag it. It will clean all that crud off your wire and make it real easy to solder. Now, I want to show you another tool you need. This is called a kilowatt. You can get these at just about any major hardware store for around 20 bucks. And what this device will do is it'll measure the voltage coming in, it'll measure, and it'll tell you how many watts, whatever you plug into it is drawing, amperage, VA, and power factor. The biggest concern that you're going to have is amperage. What are these fans drawing for current? That tells you basically the health of your fan. Do you have any shorts in the winding? You can figure that out with this, and it's a tool you really need to have.
Do you put that in series with one of the, or how do you hook it up?
You plug it into the wall, and you plug in your fan into this.
Oh.
Another tool I want to show you, this was made for me by a really cool friend of mine, Mark Allen.
Bill, on that kilowatt, if you had tried it with lower voltage, if I use the Marriott on it, mine doesn't measure. I don't know if something's wrong with it or not.
Well, the device itself, the kilowatt, needs power to run. There's a circuit in there that monitors your current draw. And put this before the Marriott.
Okay.
Yeah, this will be your first step. A little bit about me though, I was a professional electric motor rebuilder for 20 years. That's where I get my skills. And in the motor shop, when we'd have a motor come in, we had something that was a series tester. We had a bank of heaters that we could put in series with one of the power lines. So, what you'd have, this is your hot, and then we've got a heater here. Neutral. And that's basically what the circuit is on this device. And I have a toggle switch which will jump this heater out and give me line voltage out of this outlet. Now,
Question.
yeah,
Go ahead, Dan.
Can I come up and see? I can't see from here.
sure, come on.
You want a chair to sit on? Do you need a chair? Or do you want to just stand up there with Bill?
Whatever you want to do, Johnny, it's okay.
You can do either one. You can either stand up there or you can sit in a chair.
Do you mind if I can stand up?
You're fine. Be my helper. Notice how I can just hit these together and I only get a little spark. If this was plugged directly into the wall, you know what would be happening right now. What's going on is we have this heater that's within this cage is in series with this cable or this outlet coming out of this device. So that's a 600 watt heater. That's the most amount of current that can flow out of here, which is about 5 amps roughly. And with that, we just bought this at the flea market.
Whoa!
Paid too much for it. And we want to check it out and make sure that it works. So, if there's something wrong in here like a direct short,
Yes, it works!
we would know. Now, the fan might not run up to full speed. You know, because we are limiting, we're going to lose some voltage doing that. So I have my switch then after I'm satisfied that I think nothing's going to blow up, I can go up to full voltage. You hear how the fan just decided to go faster? That's because we took the heater out of the circuit.
So what happens if there was a short?
If we had a short, this heater would come on. Another thing that you can do,
So it'd start getting red.
yes, you could get a large light bulb and use that, or you could put a small light bulb as an indicator bulb across this to tell you right away there's something wrong. That light would come on. So you could essentially add a lamp right here. You know, tap in at these 2 points. You know, and add your light bulb that would come on and tell you we have a problem. Now in the motor shop, I had a bank of heaters where I could go in, I could dial in from like 25 amp load all the way up to 50 amp load. Because we worked on some big stuff. Now another critical thing that we're running a test for was working. You take one of your leads and you touch it onto that frame with the switch on and make sure that we don't see any little sparks there. Or you know, you could have just build a tester where you have a light bulb in series, you know, just a light bulb alone, and you can see if you have any leakage to ground. You know, that means that we have a wire inside this motor that's touching ground or touching the case, which could give us a shock in a sense if we touch the fan. In the motor shop, we had an insulation tester. And what this does is throws whatever voltage I want from anywhere from like 750 up to 2000 between the winding and ground to check that insulation to make sure that it's not going to break down. On a regular motor, we're looking for 1000 volts over line voltage is what we would measure for to make sure that that insulation was safe. These things, sometimes that insulation can be bad. It can be, it can break down real easily. It's not going to handle the, an insulation test like that. That's a thing to keep in mind, Now, I want to talk about checking a winding. What I have here is a common everyday furnace blower motor. The reason I have this, it's bigger, it's easier for you to see everything. We're going to talk a little bit about how this motor works. GE big motor with a starting switch, no different than this hardly. So, and also the reason why we're dealing with this is if I have an old fan up here and I'm messing with the wires and lead wires, we can do damage to those old motors, taking them apart. So this was $3 at a junk sale. Do I care about it? No. What we have in here is two windings. A lot of your Emerson motors work this way too. The early Emersons that have starting switches, they're all no different. We have a main winding, and then we have a starting winding on the inside. The main winding is this heavy coil on the outside, and these little lightweight coils here are your starting windings.
Can I see them? I can't see.
You see those? There's your startings, there's your mains. Something this motor has that a lot of old motors don't have is called a thermal protector. That's this little device sitting here that monitors the temperature of that winding at all times. Should this become overloaded or it doesn't start for some reason, that thermal protector is going to shut this thing down once it reaches a certain temperature. That's something that we can add to our fans. You can buy these one-time thermal fuses that come in different temperatures at an electrical supplier and tie one down to the winding to monitor the temperature. This is an automatic resetting device, but the thermal fuses you buy from an electronics supplier, they're one-time, they trip, and if it trips on you, there's probably a reason why. You're going to want to take that fan apart and find out why. Okay, so a little bit about how this works. As the motor increases in speed, we have a thing called a governing device, or rotating mechanism, another term for it. These little weights fly out, and you see this little barrel goes down. What happens is, we have a set of contacts back here, and after the motor gets up to speed, it separates the contacts. The starting winding only stays in the circuit until the machine gets up to about 3/4 of the nameplate rated speed, and then the your starting winding is going to be shut off by this device. Fans work the same way. And what you'll find, something you can do, if you have, like say an Emerson, for example, doesn't want to start, you don't want to know, you want to know why, what you can do is you can take your ohm meter, and in the back of the Emerson, you're going to find something that looks like this. It would be perfectly round. And what happens is, the Emerson starting device, on the rotor, there's a little piece, like little two half-moon discs that are held together with springs. And they short these together to complete the circuit for the starting winding. You could take your ohm meter and you could go in there and measure across these 2 points. And what will happen is, since we're hooked up with like this, we've got a main winding, okay, there's our circuit in there. We got our main winding, we got our starting winding, we got our starting switch. So if I go across this with my ohm meter to check for circuit for continuity, it's going to go through the starting winding and the main winding. But if that measures like it's open, we know we got a problem somewhere that has to be fixed. That's the easiest and quickest way to check that. Okay. So an ohm meter, voltmeter, handy tool to have. Now, we got our winding. We're wondering, is it shorted? Because we checked, it's drawing a lot of current, so the fan's pulling a lot of current. What we can do to find out if we have a shorted winding, we hook up our stator to this current limiting device, take a nut driver and go in here, and go around. I want you all to see this. And we're looking to have equal pull. If I have a shorted turn here, all I need to have is one shorted turn. Where two of these wires short together, I'm going to lose a lot of pull on that coil, and it would make it really weak. So I was fortunate enough to find a shorted motor here. This one's shorted. I have good pull there, nothing there. Really weak here, really weak, good pull. That's shorted.
So that pole is shorted, right?
Yeah, we have a short somewhere, and sometimes a short in this coil can also affect other coils, because this is a multi-speed motor. But anyways, we do have a short in this winding, and that's why we don't have equal pull all the way around.
Like a screwdriver?
Remember, tests like this with power, don't be doing it unless you're really comfortable with electricity. You know, I don't want to read about you in the newsletter. You know what I mean? Yeah.
So if you find out that there's a winding problem,
Mm-hmm.
and you want to do something before you just say, I'm gonna go have it rewound.
Mm-hmm.
Is that correct? So would you look for an open?
Opens I can find. Something you want to get. The number one motor that I find opens in is Emerson's. If you have an Emerson fan, blades are screwed on. Probably all seen that. It's a left-hand thread. That means you're going to turn this clockwise to get it off. And you know, you got to hold that rotor to get that thing off of there. And what a lot of people wind up doing is they wind up sticking a screwdriver or whatever they stick in there right through the winding, and they leave a starting winding. Because an Emerson has a starting winding just like this. And what you can do is you can look at this winding, and like say for example, I find 3 broken wires all in the same spot. What I'm going to do here are our 3 broken wires. They're sticking out of our stator. We have 3 here, we have 3 here. This one is going to go back to, and this one is going to go, is connected to the rest of the motor. And we have, well, let's just say we have 2 broken wires, okay? We don't know where these go. So I come in here with my ohm meter. I'm going to take it, and what I'm going to do is I'm going to take them, and the 2 power wires coming from our stator, I'm going to short them together, twist them together, help somehow. Maybe I get some test lead, alligator clips or something. Little test leads, they're handy to have. Get a couple. And I'll hook one lead of my meter, or I'll use this, and I'll look for sparks, because what I want to find out is which one of these wires here, see this one here goes back to the motor, back to the coil, back towards the plug, and this one goes back towards the plug right here. I can see that because, but in a real world in a stator where I have 2 broken wires sticking up, I don't, I just have these wires and I want to know, okay, what do I need to put together? So, measuring back at my plug, right here, where I'll short these together, and I'll connect that up to the meter. Here's my other meter lead. And this kind of winds up eventually there, and this kind of winds up eventually there. If I touch one of my probes to this wire here, my meter's going to beep, or it's going to tell me a resistance value, or however it indicates. So I know that this is one. I'll put a dot there because I know that one has power coming to it. I mean, I know that goes back to the motor. Now, I'll check this other one, and that one will be, you know, because I know it's going back to the motor. Now I gotta figure out what I wanna do, what goes together. If I put this and this together, I'll complete my circuit. If I, like, say a 1, we're gonna number these here, 1, 2, 3, 4, okay? So if I put 1 and 3 together, I'll have continuity, but if I put 2 and 4 together, I've got a short now, one shorted turn. That motor will burn up and it will draw lots of current because we have that one shorted turn. So we gotta figure out what goes together here. So I measure between 2 and 4, I have a circuit. But I don't have circuit back to the plug, you see? So I know that that's a circuit, so I'm gonna add this, you know, I'll connect lead number 4 to number 1. So I got 1 and 4 together. And I'll put 2 and 3 together. And it'll work then. And you can consequently do that if you have more opens as well, you know. Say we had another one in the 5 and 6 in this together. All we're trying to do is complete that wire, that circuit, going around and around, and making sure that we don't wind up with like 5 and 6 connected together, because then we'll have a shorted motor. Any questions about that? Kind of understand what I'm talking about here? We're looking to prevent a short, like one wire connected together like this within the motor.
If you had 4 in a row like that, if you got, let's just say, I guess 4 and 5 and then 1 and 3 mixed up, how big of a difference would that make?
As long as you don't wind up with like 5 and 6 together, or 4 and 2 and 4 together, you're okay. You know, I mean, I could start here, you see, 3 comes from the coil, you know, we know that's on the power side. I could connect this up to either, like this 3 here, I could connect it up either to 5, or I could connect it up to 2. It doesn't matter the order of how we get those broken wires together. It's just that we complete the circuit and we don't wind up with anything like that, is what we're striving to do.
But Bill, let's just say for most of us that don't really, this would be a little bit over our head trying to see wires that we'll just say are snagged or put together. Wouldn't we just first look to see if the coils are hooked together? I mean, we can physically see those wires. And if those are unhooked, can't we fix that right there? Or wouldn't that be something we can put our own meter on?
You mean broken wires?
Yeah, like-
That's in a sense what I'm talking about.
Well-
Fixing broken wires.
Well, but I'm talking about one wire that connects 2 coils that you can actually see as
Yeah.
broken. That would be real obvious to a lot of us.
Right, yeah. And you can
Okay.
put them together
And you can hook them, you can scrape the varnish off of them, right?
with that little tool I
With that
showed you.
little tool you showed me, and solder those back together.
Yes.
Yes. Instead of taking that thing to the motor shop.
I want to talk about another thing. How many people here have heard, I gotta have my fan rewound for 110 volt, it's 230 volt? Heard that before? No. You don't have to. We have 4 coils in series. Let's say we have a 1550 RPM shaded pole, okay? It's 230 volt. Our windings are connected up, kind of like this. We've got a reverse of polarity on every other coil. Okay. We got 230 volt coming in. These coils are wired in series like Christmas tree lights, okay? We're gonna drop, well, we'll make it 40 for easy, 240 volt. We're gonna drop 60 volts here, 60, 60, 60, 60, okay? So now what happens if I cut this wire right here, this jumper, and instead of this jumper going from these 2 coils together, I take this one, and I come down here to this line, and I come up here, it's in the wrong perspective, yeah, and I take this one, and I come up and connect it here. This is a cut, you know, we cut this wire, okay? You see what I'm doing here?
It's open now.
Yeah, this is open, we cut that wire. basically, we can throw, let's see here, 220 volt, 120 volt. And we split the motor in half. We're gonna drop 60 volts, 60 volts, you see? We got a 120 volt circuit there. So by cutting that in half, you see what I mean? We can make that wire, that 230 volt stator, to run on 120 volt. Or,
But how would it, how would that affect your starting torque if you're just using two coils on one side?
we're using all the coils. You know, let's draw another diagram here.
Erase that.
And they wouldn't be parallel or across from each other?
Erase
They would
that
be-
open part there.
Yeah, I'll draw another diagram, make it easier for you to understand.
Could we get the young lad to move to the right?
Yeah, you're gonna have to step aside there.
John,
Okay, Johnny.
Thank you, young man.
See, I have two separate circuits here. I have a circuit coming up going through these two coils, and then I have a circuit going between these two coils, you see? And what I have then is two, so I'm still gonna drop 60 volts on each coil. So that can be reconnected. And it's basically finding that center tap, taking those two windings out, you know, that tap or the jumper between these two coils, opposite, you know, where the power comes in. So we have two coils in series, and we can split that up and,
Does that double the amperage?
it will, yes.
So how does it handle that with the wire range?
Well, you're gonna, in this circuit here where we have it hooked up with 230 volt, like say for example the fan draws 1 amp. We're still gonna have 1 amp of current going through this one side and this side, but the total current will add up to 2 amps now.
I see.
Because when you cut the voltage in half and you know, your amperage is gonna go up.
That's why wattage works out so good.
What?
That's why wattage works out so good to measure it.
Yeah, wattage is gonna be the same no matter
It'll be
what,
the same.
no matter what voltage you run it on. That will be the same.
and just one question.
Yes.
Where can you get an antique portable fan kind of like this? Because now I want one.
Well, you gotta talk real nice to one of your parents and go in that other room.
Hook you
Yeah. Phase motor, I'm gonna talk a little bit about the shaded pole motor, how that starts. Right here, it's hard to see, we have a shaded pole, and that's one turn of wire wrapped around the edge of this pole here. That'll give us a rotating field. I'm not gonna go into the details of how that works, but anyways, say you got this on the bench and you're gonna put your fan together, you've got your GE there, it's a shaded pole, and you're wondering, well, which way do I put my stator in? The shaded pole is always on the side of the coil of the direction it's gonna go. You see that? This fan motor will turn this way clockwise looking at this end, because the shaded pole is on this side, on the right side of the coil. If it was there on the left, it would go the other way. There are some shaded pole motors, like on your 1960s box fans that had all the options. They had two sets of shaded poles, and they wound like maybe 10 turns of wire here, and they put that all in series, you know, the shaded poles to go clockwise, and the shaded poles to go counterclockwise. And you had a common lead coming out, and you connect that common to which respective shaded pole set you wanted to run for the direction that the fan would run. But this here is a single direction motor. We just have one shaded pole. Now, you got your fan, you plug it in, you check the current draw, it's running real good, and it buzzes at 60 cycles. What can typically cause that? On a lot of these older fans, the shaded poles, they generate a lot of heat, and they can break down the varnish Well, to back this up, when a motor's wound, it's dipped in varnish afterwards, and that varnish holds all these wires together so that they don't vibrate. And that can break down over years, you know, it's 100 years old. And that shaded pole can buzz, it can make a buzzing noise. And what you can do is you can get some of this red insulating spray enamel, or you can get motor varnish from an electric motor parts supplier, and you can just basically recoat this. And what that will do, it's good for your motors to do that when you're rebuilding a fan, because it holds all these wires together so that they don't short out. And it also can cause these shaded poles, it can hold them in place so they don't vibrate. Now, some people say, well, yeah, it's shorted out, I can spray it with varnish and re-insulate it, it's gonna work again. That's not the case. All that varnish does when you have a good winding is it will protect that winding to keep it running. It's not gonna fix any shorts by spraying varnish on a short winding, so keep that in mind. Okay, I'm gonna talk a little bit about rotors. You see all these little slots here going from, going across the rotor? There's a winding in there. And on an old motor, typically what they did was they pressed copper bars through the holes in these laminations. This rotor is made up of like sheets of metal called lamination steel, and they're all stacked together. And on an old fan, I had an old rotor, it never got in the car, but there'd be a brass ring around the outside, and all these were soldered together, you know, to make, you know, so we have a circuit. And there's a lot of current that goes through this. And now say, for example, you throw power on your fan, and it wants to go, and it stops like right here. And then, you know, you give it a little push forward, and it just kind of wants to jump right back to that spot, or you push it the other way, and it goes ahead and it stops, but it always stops and right in the same spot. That's kind of an indicator that you got a bad rotor, a problem with this. And then, you know, say this is a 4-pole motor, you turn it 90 degrees, and you see the same thing happen again. Turn it another 90 degrees, and it wants to stop in that spot too. That's an indicator of a bad rotor, and there's really only 2 brands of fans that I've encountered that with, mostly. Teslas and Westinghouse pancakes. And what it amounts to is getting the torch out, going around and soldering that brass ring to all those bars, touching up that solder joint. If you look on some of the older fans, you'll see solder all the way around that. Looks like a brass ring on the end of the rotor. New motors, it's aluminum. They just pour aluminum through there, and this is an aluminum ring that completes that circuit on the outside. And now we want to check that. We want to find out, do we really have a problem? Here's a device called a growler. Now we're getting more into some of the advanced things. If you can find a growler at a flea market, they come in handy to have. Set that on the growler. And I don't have a saw blade, but a saw blade would be, oh, this might work here. Do I have anything metal? Anyways, what we would feel for, this might work. When I lay this on it, see, I got some pull there. And you know, you turn the rotor and you go by the next bar, I have pull. Go to the next one, I've got pull. And what we're doing, this is like a transformer now. This is my primary, this is my secondary, and I'm inducing that magnetic field onto these bars that are in contact with the growler. The current flows up, and it's going to take the shortest path, and it's going to go around like this to complete a circuit. And that's why I get the magnetic pull where this little Allen wrench will pull up against that bar. Like say I'm turning, I'm going around, and all of a sudden I find a spot where there's no pull. I know I've got a problem with that bar. I don't have a circuit there. And I know the rotor has a problem. Okay, another way motors are started. Capacitor run. Instead of a starting switch, we have a capacitor in there called a run capacitor. Now, you can check these using our current limiter here. Just go across that. You see how that held a charge? know that's good. Another thing to keep in mind, if you're troubleshooting your fan that's not working, that has a running capacitor in it, this is an old style one, these things can hold a charge for a long time. So you might be working on your fan, you're trying to figure out why you're tearing into the switch, and you get across that thing, it's gonna jolt you. So anytime you encounter one of these, when you take the fan apart, have it unplugged, short that out, leave the charge off. In a situation where that could happen, I could have that capacitor right there, a main winding, a start winding. My main winding is open. I plugged it into the wall, and all I had was circuit through my starting winding. This could charge up and stay charged, and you get a little jolt off of it. It's no fun getting shocked. So when you take that base apart, short it out.
Bill, how did you test it again?
What I was doing is I took my leads from my current limiter here. I've got the resistor in the circuit.
Right.
I just basically went across it with the 2 leads, charged it up, and I get a spark. If you separate this on the AC sine wave, where, the AC's at 0, and you take it off, you're not going to get any charge. So do this a couple times, and eventually you'll get it where you're at your peak and get this thing fully charged. And you look for that spark to happen. There, I got it. I released on a, upward of the AC. We charged it. And if you're ever doing that and you hear this thing make a noise, almost like inside the capacitor, it's shorted.
Do you test it for voltage or ohms or continuity or?
It's basically a quick check for continuity. You could get a capacitor tester out and you could measure the actual capacitance in this. But in a shop setting, we didn't have time to do that.
All right, they're in microfarads, right?
Right, yes.
What is a microfarad?
It's a measurement of capacitance.
Okay.
The higher the MFD value, the more capacitance this has.
It's 1/1,000th of a farad.
And a farad is a big capacitor.
Bill,
Yeah.
in the old days, we weren't real savvy on that, but we'd get a continuity meter. First, we'd short them out like that.
Yeah.
And then just put the 2 leads across in the continuity, and it would go up and come back down.
Right.
It was charging the capacitor, right?
Yes.
So that was our test to see if the capacitor was good.
Yeah.
I don't know if that's exactly 100%, but it gave us an indication.
See, that works good, like in a radio environment and things like that, but the problem with that is we're not throwing any high voltage at this capacitor, like a working voltage. It's lower voltage. And what a capacitor is let's say, for example, you have like a layer of tin foil, a layer of insulation, another layer of tin foil, and we roll it all up and we stuff it in there and it's filled with transformer oil or capacitor oil, okay, as an insulator. And that's all it is. And what we're looking for is to find out, do we have any shorts between those two layers of tin foil? One layer is connected to this pin, one layer is connected to that pin. That's all that's in here. Now, on these old capacitors, there's a possibility of them having PCBs. Question?
Oh, no, I'm just waiting.
Okay. PCBs, they're bad for your health. Y'all know what that is. This may have PCBs in it. You don't want this in your house because if one of these capacitors goes bad, they can smoke, they can leak oil. Get rid of them. Get yourself a new one. And you'll see on a lot of the new capacitors, I might even say it on here. Yep, no PCB written right on there.
And isn't the capacitor to replace that one real littler than the one you got in your right hand?
They are a lot littler, yes. And just don't go out and, like go to the electronics supplier and buy any capacitor. It has to be an AC capacitor. There's a difference. Most capacitors, like in a radio or a television, they're a DC capacitor, and you can only charge them positive and negative. This capacitor is designed where I can charge it either way, reverse the wires, because basically AC is electricity flowing in one direction, stopping, and flowing back the other way. Can't polarize AC. It's constantly changing direction. And you have to have a capacitor that's designed to handle that. And look on there, it will say that it's an AC capacitor. The MFD value, you want that to be the same of whatever your old capacitor was. You know, you can maybe go 10% either way if you can't get the exact value. But the one critical thing is the voltage rating of these capacitors. You need to make sure that you have the same voltage rating or higher on the replacement capacitor, and it has to say AC.
Bill, what's the difference between a start capacitor and a run capacitor?
Okay, there's two differences there. Some electric motors, your commercial motors, your big industrial single-phase motors, are going to have running capacitors and starting capacitors. And what you would have in there, starting capacitor would go in series with this switch. And we would have something like this. Let's just call this up. This can be our run cap, okay? And we've got, let's say, a 5 horsepower single phase farm duty motor sitting here that's running. It's going to have starting and running capacitors. And we might have 50 microfarads of running capacitor that's always in the circuit. And then to get the load started, we got our starting switch. And we got a bank of capacitors over here that's maybe 400 microfarads. Now, if I were to leave that 400 microfarad of starting capacitor in the circuit and the motor started and it kept running, after about a few minutes, that starting capacitor is going to explode. I've seen that. I just heard ask me how I know. Starting capacitors are designed for intermittent use to get that motor going. They're about the same size as the run capacitor, but they're just designed to get that going and then be out of the circuit. The run capacitor is designed to be in the circuit all the time, and that's why it's physically a lot larger. You know, so I might have a 200 microfarad starting capacitor be the same size as a 10 microfarad run capacitor. It's a difference in the duty cycle, how long it's designed to be in that circuit.
Will that thing make a lot of noise if it's gonna go bad? Capacitor will like buzz?
No.
No?
But, say for example, my contact stick, that can happen. These contacts can get welded together after time as they break down, or that rotating mechanism that I talked about, that governing device, never kicked out. The motor's going to make all kinds of noise. It's just going to buzz really loud. It's going to vibrate real heavy. It's going to draw a lot of current. And that's where hopefully whoever installed it provided the right overcurrent protection to shut it down before the capacitor explodes.
Oh, because that could happen.
Can happen.
Capacitors make really neat party poppers.
They do, because, like I said, we have that roll of tin foil and insulation in there. When they explode, that usually goes flying up in the air everywhere. You would know. And I will say, when I worked in the motor shop, sometimes that was recreation outside, behind the building. Okay, now I'm going to talk about DC motors. What we would need to make this run is we need to have something called a bridge rectifier. Bridge rectifier amounts to being 4 diodes, and if we can look at a diode as a gate. This is a symbol for a diode. If I have a single diode here, I connect this up to my AC. There's my power source. And I measure here, I got 120 volts AC I'll measure 60 volts DC. And the reason for that is, if we look at an AC sine wave on an oscilloscope, it's going to look like this. This is on the screen of the scope, and this is the line in the center. And what an oscilloscope does is it gives you a picture of what is going on inside a wire. It shows the voltage coming up. We can look at the time constant that it takes for that voltage to come up all the way to peak. And it's going to turn around, it's going to drop down to nothing, and then the current is going to reverse and go back the other direction, flow the other way, and it comes back to the 0 point again. Now, if we were to measure, Rod, what's a peak on 120 volts? Isn't it about 170? Peak
160.
160 volts. If I was to apply DC to my scope, a scope is almost like a voltage meter, but it shows you this on a picture on a screen. There's RMS voltage and there's peak-to-peak voltage. On AC, 120 volts, if we were to measure just at this little time constant right here, right when the AC is at the peak, we would measure about 160 volts right there. But if you notice, this is 160, you know, this is about 80 right here, this is 0. RMS voltage is an average of all of this averaged out, which comes to about 120 volts. Okay, and that's what we're dealing with. Now our diode, it allows the current to flow this direction only. So I hook it up to the AC, the current flows this way, then when it flows that way. When it wants to flow this way, it can't go through that diode backwards. It can only come through it this way. So now what we've created is half-wave DC, where if we were to look at that on a scope, here's our 0 reference, it would look something like this. And then, you know, basically this lower sine wave is not there. And then over here we'd see another. That's half-wave DC, and that will give us that 60 volts DC. Now, if I have a bridge rectifier, which is this little affair right here, I'd apply my AC to these 2 points. I have 4 diodes, and they're usually arranged inside a little cube with 4 terminals. And you'll look on there, it'll say AC, AC, and then there'll be a plus and a minus. And let's see, we're flowing this way, so this is the plus, and this is the minus. You'll see that on the bridge rectifier. These 2 points would go to our DC fan, and this would go to AC. And if you look, the current can flow this direction to give us minus whenever we're swinging up one direction. And when the current flows the other way, the negative can, you know, if you look at this like a gate, we can only, our current can only flow in one direction, like this. So essentially what that bridge rectifier does is it allows us to get something that looks like this if we were to look at it on the scope. It would be DC, but we're going to have, you know, little areas where our voltage drops down to nothing. And we can run a DC fan that way. Inside that, yes.
Why is there a camera there?
Every time I speak to people, I like to watch it later and I like to look at it and say, what could I do better next time? So I'm going to look for all my mistakes in this talk and I'm going to look for what sounded good. So next time I do it, it'll sound better.
Good question.
Yeah. This here is a 110 volt DC motor. Could have been used for just about any application, 1/4 horsepower. Inside a DC motor, we're going to find an armature. We got a couple field windings. This is a shunt wound motor, meaning that these fields are in the circuit all the time. Well, I'm not getting into the pole, and I could go into a big long talk why and talk about impedance, but that would get so complicated. What we can do on a DC motor, most of fan motors, we're going to talk about fan motors mostly, and they're usually series motors. That means that we've got our field winding inside the stator. We've got something that looks like this, and you'll see a coil of wire right here going around this iron core, and a wire comes in, connects to one side of the coil, and it comes out of this side of the coil, it comes around, goes to a brush holder, and then over here this comes around and goes to a brush holder, and there's our two lines that we apply our power on. So everything is in series. The field windings are in series with the armature, which goes in the center. We have two things called brushes that ride on this commutator, and what they do is they allow the voltage to get to the armature. There's a winding in here, and brushes are usually made out of graphite or carbon or some type of material that can tux. On our real low voltage stuff, like in a car starter, there's going to be some carbon mixed in with, copper mixed in with this carbon, just so it can carry a lot of current. So what can happen, commutators can go out of round because this is spinning around and it wears on there. And sometimes you'll take apart a fan and you'll look at the armature and you'll see that that's worn really deep. What we do, take this on a lathe and turn this commutator. Get it all nice and smooth. I turned this one at the last pig picking meeting on Jeff's lathe. Trued it up. And when you turn a commutator, another thing you want to watch out for is make sure that you don't ever get any little copper pieces. See, there's bars here on this commutator. There are little segments. You want to make sure that those don't get shorted out. And maybe you got an armature, it looks good, but it's dirty. You want to get in there with something like a pick and clean all the carbon and junk out between these bars. And the reason for that is you don't want that to short out. If we were to look at the circuit for that armature, we're just going to draw, say we had an armature that only had four commutator bars, which is not possible. Usually there's 40 of them. We have a winding in between every bar. Sometimes we can have a break in one of these wires. Okay. What you can do, this is not the greatest test in the world, and I'll explain why in a minute. We can take our ohm meter and we can measure between two bars next to each other, and right now I'm measuring 0.9 ohms. I go to the next one, I measure 0.9 ohms, hopefully. I got 1 ohm, oh, now I'm 0.9. And go around and make sure that all of those are somewhat the same. If you get to a point, all of a sudden you have say for example you had a 10-bar commutator and you're measuring 1 ohm at each bar, and all of a sudden you measured 9 ohms, you know what's going on there? We'd have an open right here, and when I put my probes here and here, instead of measuring through this coil, I'm going around through all of the currents, the voltage from the meters going around through all the other coils, and that's why I'm measuring a real high reading. We know we have an open there, an open in one of the coils in this armature. You can see all these little windings, and they're all connected and tied into this. Now, in a shop, I would have put this armature on a crawler. And if I had a saw blade and I was prepared, I'd go around and I would check. See how this is sticking now? I've in a sense created a short by shorting two of these bars together. I remove the short, doesn't pull down, create a short. See the difference? So when you're going around and you're spinning your armature around, and all of a sudden it sticks there, you turn it a little more, it doesn't stick, you know you have a short. And that's where you're gonna wanna come in and you're gonna wanna make sure that all of these bars are cleaned out. There's no debris between the two commutator bars. Try that first, then go back on your growler and see. And if it still sticks, you may have a short in the armature. And all you need is like one turn shorted together, and it will cause this thing to not work. Symptoms of a shorted armature: you turn on your DC fan, it wants to go a little bit, you get in a certain spot, and it kind of gallops when it turns, it just kind of jerks as it starts to go, draws a lot of current, might release a little smoke. That's a sign of a shorted armature. Now, if we want to make sure we don't have opens, the way we did it in the shop, we would take something like a nail or something, go between each bar, and I would see a little spark there as I'd strike each one. And then I'd know that with each spark between each bar, I know that coil's good, that coil's good, that coil's good. Some growlers have a meter where you can sit there and you can hold two probes on there and you can look at the meter and it will all, okay, I got 2 amps, 2 amps, 2 amps, 2 amps. A professional motor shop, we need to make money. We don't have time to do that. So if you don't have any pull and you just get a spark at each one, you're good. Okay.
Bill, you said that you turned that on the lake.
Yes.
So obviously you're gonna have a smaller diameter, so then do you just have larger brushes to accommodate that gap?
Well, sometimes yes and no. A lot of motors, or big motors, there's a little screw right in here, and you can loosen that screw up and you can bring the brush holder closer to the commutator then, to compensate for the wear. But typically, when you're turning a commutator, you're only taking off maybe 20 thousandths. You don't have to deal with moving a brush holder for that. Yeah.
You said saw blade, you meant like a hacksaw blade?
Hacksaw blade, yes. Hacksaw blade. You want to shop, every growler's got a pile of worn out hacksaw blades next to it.
Generator, armature, or starter armature.
Sure.
So, and the same thing, the boss would always say, make sure the grooves are cleaned out.
Yep.
You need the interruption, I guess, how is that what it is?
Well, in the shop, we had a tool called an undercutter. And that's like a little tiny saw blade on a shaft. It's a tool that was made just to
It's made for that.
undercut this mica,
Yeah, like,
On a fan, it's not so critical to do that, but if you have a multiple horsepower DC motor, you want to undercut these.
Is it harder on the brushes when you do that and make little gaps in between them?
No, it's not.
Okay.
The commutators, they're pressed on, aren't they?
Yes. I want to talk about bearings and lubrication. When you're at the flea market and you're thinking about buying this fan, grab the blade and try and lift it up and down. You feel a little play up and down, you know you got wear in that bushing in the front. Sometimes you can grab it and you can try rocking it like this. You can tell if you have play in the back bushing. What can happen is they wear so much that rotor starts dragging on that field. I've had a lot of people call me and they say, Bill, I got a fan and I can't figure out what's wrong with it. I spin it over free, I plug it in, and all of a sudden it instantly stops, it locks up, and I can hardly turn it. That's a sign of that rotor coming in contact with the stator. You've got a strong magnetic field here, and that will hold that rotor still. It'll just grab it and hold on to it if you have wear in the bushings. The way you can check a bushing when you disassemble a fan, put the rotor in there, try and rock this like this. If you can rock it like that, sideways, that's an indicator that you've got some wear. Now, every bearing needs to be lubricated. And in this motor, we have something called a wicking. It's surrounding the bearing. And inside there's a little window in that bearing, a little felt tab that comes up and makes contact with the shaft and supplies the oil to the shaft to keep it lubricated. My little GE fan here, down in the bottom, when we fill this up with oil, it just sits in there and that oil wicks up to lubricate that shaft. A lot of times when you take these apart, you're gonna find that this wicking is all hard, it's got dried out oil in it, it's full of dirt. You can buy this wicking, replace it. If you're a person who does not wanna buy some new wicking, just squirt some oil on your bench and roll this through the oil, just kinda wash it out with oil to get some of that debris out of there. But I recommend replacing the wicking.
Daryl Hudson actually sells that stuff, doesn't he, the different diameters we use?
Yeah, that's one source. There may be other sources for wicking, but you wanna replace that.
You just look at mineral spirits for a while to break down all the old stuff.
You could try that, but make sure you get that all out of there before you reassemble your can. Put fresh oil in there. I like the Royal Purple ISO 68, but I hear they're not making that anymore. You can buy that oil in little Zoom spout bottles, that's good oil. I recommend staying away from automotive engine oil because it has detergents in it that can do bad things to your winding. Get that Zoom spout oil, a bottle of it's like $2 or $3 at Ace Hardware. It'll last you a few years, I do like the synthetics. I've heard some people talk about using GABS oil, air compressor oil. I'm kind of experimenting with that oil and just trying to see how it works in some of the fans that I use. What I found though, some automotive engine oils, they don't really maintain a good film strength with just a wicking, And don't skimp on oil, buy good stuff. Your fans are worth it. Okay, any questions?
I'd like to share something with you a minute.
Yeah, go ahead.
If I do fan blades, and if you look at a fan blade on a GE fan, it has a finger that the blade is riveted to. And you can look at that blade, and if it's got a shadow around that finger right there, that blade has been ran a lot. And the deeper that finger is around there, the more it's been ran. And if that finger, that blade on there, it has none at all, that fan hasn't been played with that much. Running that much.
You've seen it on the blades.
Yeah.
I gotta see some examples of that. Do you have any here?
It's nice to see.
Yeah.
Well, yeah, a few more things I want to cover. I got my notes here, just making sure I'm talking about everything. When we go back to an armature, it doesn't happen so much on fans, but sometimes these commutator bars can loosen up. And if they do, they kind of rise up and they'll spark. Another thing to look for is a telltale of having an open armature is if you look at between two bars and you see an area where there's a lot of pitting. It looks like one of the bars is burned away a little bit, That's an indicator of an open in an armature because every time that open spot comes by a brush, it sparks real big and it will burn away at that commutator.
Hey, Bill,
Yes.
how do you know the tension on the spring for the brushes? I get these things all the time, and the springs there, somebody puts 10 springs in there, and you get a million things in there, yeah?
That's a good question. You just want it to be lightly making contact. My brushes go through. I can show you later on. We can take the spring. I can show you, just exactly how tight this would be inside a motor.
Okay.
You just feel it yourself. Then anybody else wants to learn more about brush tension, come up after the talk, and we'll
Great, thank you.
show you how that's done. Yeah, you've got your GE. You got your fan. It's a universal motor. 2 brushes. Something that can happen with these motors, don't run them with the blade off. The reason why, they'll just keep building speed, and they can keep building speed to the point where the armature can actually fly apart. Centrifugal force. I take it someone did that, huh?
How'd that little thing work out, Nick?
Say for example, you have this, one of these motors, you get done rebuilding it, you want to test it. You didn't put your blade on. Run it with a variac and slowly bring the voltage up. And maybe you bring it up to about 50 volts, half its rated voltage. That way the motor won't go run away from you and explode. Fly apart your commutator. And another tip on checking a fan, you just brought it home from the flea market. If it's an Emerson, and we have 3 head wires going down to the base, and they're hooked up wrong, and Emerson can start and run backwards. And what can happen then, since that blade is screwed on, it can come off and go flying. Now, I do know a guy in the club who bought a real nice Emerson, I believe it was a 6-blade, perfect blade, and he's running it and he didn't think, and his blade went flying, he caught it in midair. You know what I'm talking about? But yeah, that's another thing to watch out for, you know, when you start an Emerson. First thing, take a look at the direction. And something that I should have brought up at the beginning of my talk, when you get a fan, the first thing you want to do, read the nameplate, look and see what voltage it's set up for. I mean, there's DC fans that come in 32 volts, 110, 230. 32 volts was used on farms when they had these Delco generators that generated a farm voltage. You could buy fans in 32 volts, light bulbs, just about any kind of appliance you wanted in 32 volts DC. There are, sometimes you can come across an AC fan that's rated for, you know, it says it's 25 cycle or 133 cycle. There's different frequencies of AC that was used back in the day before it was standardized. If you run a 133 cycle fan on 60 volts, on 120 volts DC, it's going to draw a lot of current. It will run really slow and it will burn out. The reason for that is, now we'd be getting into talking about impedance. The higher the frequency AC that you throw at a coil, some might understand this, some might not, but it's not that critical to know. But if you run a 133 cycle fan on a lower frequency, we're not going to get enough impedance built up in the winding, and that's caused by induction. You know, a coil of wire inside a magnet, inside an iron core, and that provides you with your opposition to current flow. It'll draw all kinds of current, and it will eventually burn out. Plus, the fan would run at about half the speed that it was normally designed to run for. There are inverters available on the market where you can actually take your 60 cycle AC and convert it to 133 or to 25 cycle. Now, if you try to run a 25 cycle fan on 110 volts, 60 cycle, motor's gonna have no torque at all because the frequency is higher at 60 cycle, and it's just gonna sit there and turn real slow and not really get up to speed. So, read your nameplates. You know, you gotta make sure, yeah?
So if you have a permanent split capacitor motor, let's say it's a 24-inch more or less, you hook a variac back up to it. Since you're running less voltage through that fan motor and the blades are spinning slower, you don't have as much air over the motor, can that make them run unnecessarily hot when you have the voltage turned down? Can that be detrimental to the life of the motor?
All motors behave differently when you run them under reduced voltage. One thing I will say is never run anything with a starting switch at a reduced voltage. You can get away with it usually on a permanent split capacitor where you have, you know, just a run capacitor in a circuit. You can get away with it with shaded poles. Try it. But the big thing is, run it for a while, keep your hand on it, you'll see how hot the motor's getting. If it stays cool, you're probably all right.
You may have spoken about this in the very beginning, but if you have a basic, and in case I'm thinking about an Emerson motor, say from a junior fan, and you need to, what's your recommendation on what wire to use and the soldering means to put a new lead wire on?
You mean to connect a head wire to
Yeah.
Okay, what I recommend doing, got our little fingernail cutter, you know, clean the wires up, the magnet wire with that. And then you can get some of that wire from Antique Radio Supply or any of that reproduction wire. Solder that on there, put some sleeving over it, like either a heat shrink tubing, and don't get the, you know, like the common Menard stuff, you know, get the good stuff from an electronics supplier, shrink it, tie it down to the winding, or friction tape you can use in a winding, that's good too, tie it down, some wax string, and you can go through, if you look, on a winding, you see the wires come out of the stator, you can go tie those leads down to that bundle of wire, tie it down, And that way, it's secured, so it doesn't come pulled out of your motor.
Is that what you were doing on that tripod yesterday?
Yes,
Okay,
yeah.
all right.
Questions? All right.
Bill, just one more, just another point, but those infrared thermometers are pretty handy too for, the temperature. I don't know if you brought that up or not.
I didn't.
But, those are kinda handy, to check the heat on the motor too.
Right, and another thing, you can find out, with one of those infrared thermometers, if you can go through vent holes and aim it at certain coils, you can find out if you have a short, because you got a coil that's running excessively hot. Any other questions? Rod, anything else you think we should cover?
Brother, don't be fooled on those infrared thermometers with the little laser dot.
Exactly.
You are not measuring the temperature at that dot.
Yep.
They have a cone.
Mm-hmm.
Experiment a little bit, take like a soldering iron, something like that. Back off about a foot, aim it, it'll show hot. Start going off the side, it'll still show hot. Just cause you pull that laser off of that soldering iron, doesn't mean you're measuring the bench and not the soldering iron. There is a cone that it measures. I've seen people go through and try to, one precise little spot within an eighth of an inch and say, okay, that's the temperature of that spot. Now it's the temperature of an area about that big.
Good to know.
From what distance? What's the best distance to shoot from?
Well, the farther back, the bigger the area. It's a cone.
Uh-huh.
Okay.
The closer you get, the narrower the area you're measuring.
Okay. So it should be within 24 inches or so?
Well, it varies, doesn't matter. If you move back, the area you're measuring gets wider. Move close, it gets narrower. Now, if you're curious, just, like I said, experiment. Measure something that's really small and hot, like a soldering iron. And you'll find out if you move that laser about a quarter inch off the soldering iron, the temperature does not drop to room temperature.
Choke coils, could you just maybe 3 minutes on a choke coil, what exactly it does?
What a choke coil is, it's a coil of wire, looks a lot like a transformer. Okay, and you look in the side, the bottom of your fan. You got your 3-speed switch here. What we have is, that wiper that goes around, and it can connect to either this contact, that one, or that one. Now, this goes to our motor. This goes to line 1. Here's our motor. This is line 2. What happens here, this will drop the voltage that's fed to that fan motor. It will slow it down. We add turns of wire. This would be our high, medium, and low. High is directly across the line. Then there's medium, and then there's low. Now, some fans have 3 wires in the head wire. We have a start winding. We have a main winding. There'd be an extra coil added in here. And that would be used for, giving us a phase shift that would start the motor. Now, sometimes we run into a situation where head wire is cut off entirely. You got the 3 wires and you're wondering, where do these go? So we have our 3 wires coming from basically from, our speed control, and we have our 3 wires from the motor. And we want to figure out where they go. What you can do is there's 9 combinations by lettering and numbering. 1, 2, 3, A, B would be here, and C would basically be, the neutral coming through. You can arrange those where you can go through the 9 combinations and do it with a current limiter. And when you get that thing to run on all 3 speeds, and it doesn't draw too much current, you got it right. Trial and error.
So does the impedance change then? Is that how you tell? You look at the impedance rating on the voltmeter?
Well,
No.
voltmeter isn't gonna measure your impedance. Are you
Okay.
talking when I'm going through the combinations, putting those wires
Yeah,
together?
exactly.
The motor's basically just gonna buzz or run backwards, or it's not gonna run right. But when you get the right combination, it will work. You can figure it out with a meter, but I'm not gonna go into that, it gets a little deep. But, you know, have this in the circuit, you know, limit your current, and you can go through those combinations. Now, I will tell you though, Robbins and Myers fans, you can hook them up wrong, the fan will run right, you know, you'll go through your 3 speeds and you'll think, I've got it. May not. So you wanna check your current draw with your kilowatt and make sure it's not excessive. And, you know, typically these fans are gonna draw less than an amp. A shaded pole motor draws about twice as much current as a, you know, a shaded pole's gonna draw maybe 0.7 amps. You get a capacitor run fan, same size as this, it might draw about 0.4 amps. But you know, if you do a Robbins and Myers, and you're going, oh my gosh, it looks like it's working, you've got your resistor in there, you're gonna take it out of the circuit and go across the line, and it's drawn 4 or 5 amps, but it's still running fine, it's hooked up wrong. So that's a thing you gotta watch is your current draw. Always watch your current draw on your fans. Too much, you know you've got a problem. And if that's hooked up wrong, your motor's gonna burn out. It's gonna burn out that choke, it's gonna burn up that stator.
On the speed coil, the way to look at it, the way I was taught, an inductor, it's a coil, it's an inductor. It bucks the voltage. When you apply voltage to it, and initially, the very first thing is 0. And it has to build up. Where a capacitor is, when you apply voltage to a capacitor, it's a short initially.
Yeah,
And so that's what the speed coil does, it bucks the voltage.
say for example, I unwound this speed coil, that choke, and I just laid that wire out on the floor. Ran those wires back to that switch, wouldn't do anything, wouldn't vary the speed at all. But when you wind up wire around an iron core, that's where you get that induction going, that magnetic field being induced into that iron. That's what causes the the current flow to be bucked, and it drops the voltage going to your motor.
Yeah, it's not a resistance, it's a bucking.
It's impedance. And basically, a measure of impedance is kind of adding up resistance and also the inductive reactance within that coil. Questions?
Now, the resistance of the wire in a choke is insignificant.
Right.
He's not against trying to ohm out speed chokes. First of all, ohm was never a verb, but that's another chapter. People, I mean, and this is common thinking, well, I just measure this and I can tell if it's good or bad. Not really, 'cause like I say, if you got 500 turns in there and you got one shorted turn, you can't see that with a resistance measurement. But your choke is junk.
That's right.
Best way to test a speed choke, look it up the fan, see if it slows it down.
Yep. You have that one shorted turn, it will not slow the fan down.
And if you got a noisy choke, you can spray varnish and it'll quiet it down, right?
Yes, that's another thing that can happen is, I've seen this on Westinghouse tanks a lot. The base of the fan is buzzing when you go onto a lower speed. You can get some of that insulating enamel in a spray can, spray it down really good, and let the varnish or the red insulator get into the, all over the iron of that coil. Because what you got in there is like all these layers of laminations, one of them is buzzing, it's vibrating. And that varnish holds that in place. Or you can take the choke and dip it in varnish too, let it dry. That'll solve that problem.
So it's the plate, not the wire, that's doing and making the noise.
Usually it's a plate that's vibrating.
Alright.
And like I recommended earlier, to spray your windings, spray your chokes with an insulator. What that does is, in an AC circuit, these wires, if they're loose, they can have a tendency to vibrate too from the, you know, the AC going through there, you know? And vibrating wires are gonna wear, it's gonna wear the varnish off the wire, and we have a potential for a short. Any more questions?
Very good.
Thank you, Bill.
Thank you so much.